Okay, so here's your poll question for today. How are accuracy and precision different? Is accuracy being correct and precision is the same thing, correct? I guess that's not the answer since it asks you how are they different. Accuracy means being consistent and precision means being correct. Or accuracy means being correct and precision means being consistent. You could move your spot to different computers. Go over to the side there. All right. Whoa, you're making a comeback. The right answer is making a comeback. The correct answer is accuracy means being correct, and precision means being consistent. Okay. We'll talk more about that a little further on in the PowerPoint. Science is more correctly is done through a process of modeling, not really a strict linear process of the scientific method. So I'm not going to spend too much time talking about the scientific method because I don't really put much weight in it. Okay. But one part of the scientific method that is crucial for chemistry is the idea of being able to collect data that you observe and understanding that data comes in two different forms. You can either have qualitative data or you can have quantitative data. Qualitative data is sort of subjective. It's descriptive. If I were to ask you, can you give me some qualitative data about a tree? You might say, well, the tree is pretty. The tree is large.
It's tall.
The tree is tall. The tree is green. The tree is brown. Depending on who you ask, you could get a variety of different descriptive words for the tree. If you ask for quantitative data, though, you would assume, or you would at least hope, that you would get a lot of the same data. For instance, the height of the tree is 7.27 meters. The girth of the trunk is 1.4 meters, something like that. Okay? Quantitative data is numerical. It's definitive. Qualitative data is a bit more subjective. Both are equally valuable. Just depends on what type of research you're doing. Okay. Now, a system, just by definition here, a specific portion of matter in a given region that has been selected for study. So when we study something, we can't study every single zinc oxide molecule in the universe, but we sure can study a few million of them in the lab, right? So in the system that we study, that's what we're talking about. In this system, this is what happened. This is the data we collected from this system. A different system might have different parameters that are affecting it. But in this system, this is what happened. Okay? So if we ever use that term, let's use that term correctly. What was happening in this system? Okay? Now, the process of science that I think is a bit more true to real world than the scientific method is a process of called model-based theorizing or modeling, just modeling in general. Okay? A model is more than, in science anyway, a model is more than just a physical object. When you think of a model, you might think of a toy airplane or a model car, something like that. It's a representation of something that is too large or too big. It gives you something physical to look at, right? A DNA model of the molecule of DNA, okay? But a model can also be a set of ideas. Think about the kinetic molecular model of matter, right? Is that really a physical model? No, it's an idea, right? It's this idea that all atoms in matter are moving. They're all vibrating at some speed. And depending on the speed, that tells you the state in which that matter is in. So if they're moving slowly, that's a solid. If they're moving a little bit more quickly, that could be a liquid. And if they're really moving fast, that could be a gas, right? So the kinetic molecular model has now become kinetic molecular theory in that there is a lot of evidence that supports it. Okay? So science as a process actually is a process of generating a model, testing that model, and then collecting the data from that test and going back to the model and tweaking it and changing it so that it fits the new data. And at some point, when you start to get data that fits the model and you don't have to change it, that's when that model is on its way to becoming a theory. Does that make sense? Okay. So you could make a model, you could test it, collect some data. If the data doesn't fit your model, then you change your model a little bit until you start to get consistently data that fits the model. Okay? So then when new evidence arises, you change your model to reflect the new evidence. Okay? And so a theory is a broad generalization of all of the facts, and the model is the way what we use to describe the theory. Okay? Now, all scientists use one standard way of measuring things. That's called the SI unit, or the Système International des Units. So I can't do French, but SI units. There are 7 basic units, and anything else is usually derived from one of those basic 7. The basic 7 are length, mass, and time. Right? Length in meters, mass in kilograms, time in seconds. Temperature. The standard unit for temperature is Kelvin. How many of you ever heard of Kelvin before? Heard of that? Good. Okay. The amount of a substance is called a mole. Have you ever heard of a mole before?
No.
Okay, we'll learn that next week. What about electric current? An amp or an ampere?
Yeah.
You've heard of that probably. And a luminous unit is candela, or a measure of the amount of light being emitted. Okay, you may not have heard of that, but it's called a candela. Okay. Now there are other units out there, for instance, density, right? And we call these types of units derived units. Derived because they come from 2 or more basic units. So density here is mass over volume, and the unit is kilogram per meters cubed. But you can use, and what we will use for density in this class, is grams per milliliter. We cut it by a factor of 3. Does that make sense? Take kilogram down to gram and take meters cubed down to gram. I'm sorry, milliliter. Okay? Molar mass, these aren't going to make much sense right now because you don't know what a mole is, but we'll get to those. Okay? Now, conversion factors. Conversion factors are ratios derived from the equality between 2 different units. For example, if you have 4 quarters and $1, those 2 amounts are equal. So 4 quarters divided by $1 equals the whole number 1 with no unit, right? You have 1 of those. So you can flip-flop that and say $1 over 4 quarters, 4 quarters over $1. Either way, it's the same thing. Okay? That's called a conversion factor. Conversion factors are used in something called dimensional analysis, which is the same exact thing as the factor label method that you learned last year or last semester. Okay? Dimensional analysis allows us to manipulate numbers in terms of their units. So if we want to get rid of units from a number, we can multiply it by a conversion factor and get into a different unit. All the while not changing the amount of some substance that we have, or some material. Okay? So if you want to convert from quarters to dollars, or from dollars to quarters, you multiply the dollars by the conversion factor of 4 quarters over $1, and you end up with 48 quarters. Nice simple dimensional analysis problem.